Hey guys, welcome back to another episode of Simuleos. Today we are going to continue working on what we were working on yesterday, Determinant Visualization. Now yesterday I made kind of a mistake like I did the day before and like I do every single day on this channel, but that's perfectly okay. We are going to work on, hey Gustorn, we're going to work on, well first let's open up Zernal. We now need to work on the interior cube, and if you weren't here yesterday, you wouldn't know what that means. So let's go ahead and get started talking about determinants, what it is we want to do, and where we want to go. This should take like 10 minutes, and then we'll go ahead and get back to the code. So, here's the idea. A determinant can be determined in a number of different ways. We have the first and most obvious way, which is simply A, B, C, D, going to be equal to A times D minus B times C, right? There you go. That's your 2x2 determinant. Obviously, a 3x3 determinant is a variation on the 2x2 determinant. If you have A, B, C, D, E, F, G, H, I, it's simply going to be A times E, I, F, H. So A times E, I minus F, H minus B times D, I, FG, DI minus FG, plus C times DH minus EG. Now here's the thing, if you guys have any questions, comments, concerns, if I'm moving too quickly, let me know and I will totally slow down because I kind of covered all of this yesterday and the day before, so I don't see any reason to really do it incredibly slowly again. But if you want more information, let me know and I will totally give you that more information. Okay, but now we have a question. What does the determinant mean physically? Well, it should be, unless I'm completely off my rocker, that it is a ratio, not difference, but it is a, basically a change in the ratio, or rather a change in the volume after matrix transformation. So we have a matrix, we have a couple of points, we have a volume inside those couple of points, we perform a transformation, and we have a new volume. And the difference in volume, rather, the ratio between the volume of the new cube versus the volume of the old cube should somehow be related to the determinant. So we're testing that out right now. What we're doing is we're taking a standard cube in space, pretend it's a cube. We perform a matrix transformation to it. So we get some sort of weird, oddly shaped cube in the end. And then what we do is we do a Monte Carlo algorithm to see, hey, what is the area within and without this cube? And then after doing that, we have the areas, and we simply say, okay, now how much space do each of these cubes take up? So again, this uses a couple of things that we've been working on lately. One being the 3D visualization stuff that we've been working on for the eigenvector video. The other is the Monte Carlo algorithm that we did in the last video. Then after this, once we finish up the visualization, we've got a couple of different things I would like to do for the video, but I don't think I'm going to do that on stream. Those I don't think will take as much time, and simply use the eigenvector stuff that we used before, just using different eigenvectors. So I think that's honestly about it. All we're doing right now is finding a ratio between the areas, and though we have a lot of stuff to do programming wise, I think intuitively it is pretty simple. So again, if you have any questions, comments, concerns, let me know, and I will totally get to those as soon as I see them in chat. Outside of that, let's go ahead and show what we did yesterday. Again, I apologize for being so short with these. I know there's a lot more information I could go into, but you know, I never know exactly how much I should go into, because on the one hand, I kind of do it every day, right? And so you think, okay, if you do it every day, then surely there is some sort of, you know, someone who came yesterday would probably watch the same intro again today. And the thing is, the people who are watching right now are probably people who have seen the channel before. So I don't know. It's one of those things that I just kind of do a quick 5-10 minute thing just to kind of reintroduce a problem, and then I go forward. Okay, so projects, Simuleos. So Gustron says they're okay. So if Gustron says they're okay, they're perfect. Okay, Simuleos, what do we want? What am I doing? Oh, visualization, and then we want determinant. And I'm just going to copy this and put it over here into this terminal. You guys didn't see that? Okay, so let's see, what do we have? I think, let's see what happens if we run out.mp4. So let's run the last mplayer. Okay, so this is kind of what we got so far, in a way. It looks okay. Here's what I'm going to do. I'm going to open up the code, vi determinant.py. We go down to the bottom and let me render a movie. So let's write this, and then let's go over here and do Blender. Hey, Woody Bants, more math. Yeah, we've got it at least for the end of the day, and then we'll see how much further we go from there. Okay, so we'll do determinant. Now let's do Blender, and it should run. Oh, it runs Blender-P. Oops, my bad. I meant to run Blender-B-P, but that's okay. Give it a second to append all the frames. Oh, it's gonna take forever to append all the frames. Holy cow. Let me just close Blender for now. Oh, apparently I can't do that anymore. Oh, apparently I can't do this anymore. Oh, wow. Used to be, at least so far as I remembered, that if you press Control-C twice in the terminal, it would cancel the Blender command. This is unfortunate. How do I Control-D? Nope. I apparently cannot stop this train. It is apparently moving, and I'm apparently stuck allowing it to finish moving. So anyway, there's 80 frames. It's at 21. I don't think I can do anything but, oh, yep, dang it. Okay, so this is what I'm going to do. Run quit, kill all, Blender, and there we go. Okay, now what I'm going to do, I'm going to go here, and let's do, open up determinant.py. No, determinant.py is perfect. Let's do Blender-B-P so it doesn't open up the GUI. Okay, so let's go here. Now, it's going to take some time to append each frame. That is perfectly okay. It's going to take just the same amount of time over there. Hey, Lucky Box, what's up? So let's go here and open up determinant.py one more time, and let's talk about what we have left to do. I wrote a couple notes at the top because I knew I'd forget. We have to make the Monte Carlo spheres translucent. This is something you'll see in just a second. We have to figure out if we're in the exterior box. Again, if you saw the visualization that we showed just a second ago, you'll know that there is an interior box that we're integrating and also an exterior box that we're integrating. We have to place duplicates. I think I'm already doing the place duplicates thing, so I think I can get rid of that one. Just, here streaming. Let's see. Make particles invisible until generation frame. So we got a couple of different things to do. And one last thing I did not put down, but we do need to get done, is, oh, never mind. I did write it down. I was rendering slow yesterday as well. We didn't do any rendering yesterday. We just opened it up in Blender. I think that's why I didn't do any rendering. Rendering is going to be a pain in the butt when we go into the, what am I going to say here? When we go into the real Monte Carlo stuff, because here we only have like 1,000 particles, but when we have 1,000,000 particles, it's going to be a real slow rendering time. So I've got a way to speed that up. But that said, for the video, I think I'm just going to open it up in Blender instead of rendering the video. Here I just want to show you the latest video that we have to show that we have something that's kind of sort of working. And then I'll kind of explain what it is we want to do after this guy is finished rendering. Now, that said, we can go ahead and get started. We know some things that need to be done. Let's go here, and there should be a new sphere command. So let's see, new sphere. Yes, this one right here. What we need is a new sphere for Monte Carlo. So let's go here and put down new sphere for Monte Carlo. So I'm going to do the same thing we have before, new sphere, then say Monte Carlo. What is the difference? Well, the difference here is that we're going to have to make these spheres translucent, and we're also going to cut out the number of segments. So before we had 32, let's drop this down to 10. No, I guess still keep it a power of 2. So I guess we'll turn it down to 8. They'll be incredibly just ugly looking points, but I think that's okay. So we have 8 segments. Now let's go through and see, how do I change the color to translucent? Let's see, that would be in the materials. So let's see. we have me.materials. Mat is equal to create new material. So how do I make something translucent in Blender? That's the question. Translucent Blender. Materials, what is between translucency and transparency? Transparent, reflection, translucent. Okay, so what do? Transparency allows light to pass through without refracting or scattering it, while translucency scatters light to some degree. Okay, so I guess translucent is what I want. Translucent shader is more likely to be a refraction shader with a high roughness. So here's what I'm going to do. What? I think the naming conventions are okay. I don't know. I'm just adding a Monte Carlo to the end of everything. Again, I apologize. So let's go here and I'm going to run the last mplayer command. I'm going to full screen this. Okay, so now you can kind of see what we were getting at before. Okay, so we have a large exterior box. Then we have this interior box here that we're trying to integrate with, and a middle box in the center there. Now, here's the thing. When we do the actual simulation, there will be a heck of a lot more points, and there will be, they'll be a little bit smaller, and they'll also be see-through. So this will mean we are not, I guess, occluding data in the center there. We've got a lot of stuff we need to get done today in order to get to the point that I want to get to. And so I'm kind of deciding how we want to do what we want to do if we don't get there, but I guess we'll get to that when we get there. So the reason it took so long to render is because we've got 1,000 different objects that we're rendering every frame. I have a couple of things that I can do to speed that up. The first of which is the obvious one, which is do not allow points to render until they need to be rendered. And that's going to be something that we do in just a second. The other thing is I need to create a special texture for the Monte Carlo stuff, and then we can go from there. Okay, so let's go here. Wait. Yeah. Oh, am I not supposed to capitalize proper nouns? Huh. I always do. It just makes sense, because otherwise I forget that they're not capitalized, and then I don't know. Anyway, it's fine. So now we're going to run blender-p, not -b, so we're not going to open it up in Python. You're sure the interior box detection is working fine? No, I think it's just an optical illusion. We'll check that in just a second. Let's go here. Let's run that, write this, go here, and let's run blender-p. Now this one takes significantly less time. Let's now move this giant box out of the way, and let's zoom in real quick. And I think, if we zoom in a little bit further, from here, it's kind of hard to tell, but I'm fairly confident in saying that only red particles are in the interior box. I think that's fine. Okay, so here we can see the matrix being transformed. Everything seems okay. Okay, so we're going to be opening it up in Blender quite a bit from there on. Yeah, I mean, I've got a weird style, I admit it, and I think everyone who watches this channel knows that it's not standard, but that's okay. So we are not going to be rendering the movie anymore this particular video until maybe the very last bit. Okay, so let's go ahead and keep working on that. Oops. Let's go ahead and keep working on the MC texture. So let's bring this down here. And let's just grab one of these points at random. It doesn't really matter which one. And now let's go over here. And let's see what we need to do to make it transparent. So here we're there. But what I want to do is, let's see, wire volume. No, what do I do to make it transparent? I've used IDL, not SDL. Okay. Let me see. Let's go to material here. Well, that didn't seem to do what I thought it would do. So I know one thing we can do is volume render it, which is fine, but I feel like that might be going overkill for this one. So like I could lower the density to be something like this, and that's fine. But again, I really feel like that's a little overkill here. How do I add alpha values? That's what I want, transparency. Good, okay. So we'll just add in a transparency and set the alpha value to be something. So let's see, what is this here? Transparency. Python data materials MCB, use transparency. Good, and then we'll set the alpha to 0.5. That's all we need to do. So let's go over here. And when we create the initial, what do I want here? Yes, MC red, MC white, MC blue. we should be able to go through and fix it up. So here we have MC red, and let's just do what we are told to do by Blender. So bpi data materials MCB use transparency. Bpi data materials. Oh, my bad. MCB. Oh, MC red. Sorry about that. Then I think it's use transparency. Let me see. Use transparency, correct? Dot use transparency equals true. Now I don't remember in Python if it's capitalized or lowercase, but we'll see what happens. So now the next one is down here, the alpha value. And right now I guess we'll set it to 0.5 and we'll see what happens. So bpi data materials MCB alpha. Good. So bpi dot data dot materials MC red this time, MCR. Then we do alpha equals 0.5. Okay, and now we're going to be doing this for the other two spheres. Here we are. 1 second there. And of course, there. Now the new sphere needs to be changed to new sphere Monte Carlo, which again is just going to change the number of vertices, so maybe it's not as necessary as I thought. Let's go here. Okay, so now let's see what happens if we run this one. We're going to do Blender-P. It does seem to run. Okay, so now if we go over here, it should be that these circles are way less defined. Yes, and you can clearly tell that they are way less defined. However, they're still circles, and because they're going to be much smaller in the end, it's not going to be as noticeable that they're incredibly small. So I think that's okay. In Python, everything should be all lowercase, separated by underscores, except classes which are in Pascal case. My apologies. I'm leaving this for now. Okay, 1 second. Let me get a quick sip of water, and then we can keep working on it in a second. Okay, so that seems to be okay. Now what's next? Next thing we need to do is give every single one of these points a time at which it's going to appear. Use transparency. Oh, I was talking about true, the T in true. Sorry guys, I hit the microphone a little while ago. I didn't know if that was a lowercase or uppercase, so I just kind of guessed. It's a lowercase in C++, but uppercase I think in Python. Okay, so let's do x equals random box length. So this is us giving it a random position. Then we're giving it an ID. So now what we need to do is give this ID some sort of keyframe to appear at the frame that we want it to be at. So let's see. We have total count plus 1, print I. We return the frame number. So I guess inside this guy we need to increase the frame number. So let's go here and say frame number plus equals 1. Okay, so now we have to add in the appropriate keyframes. 1 second. Keyframes. And you know what I was thinking, guys? This guy should probably go under here. So let's do, what was I saying? I just had it, frame number plus equals 1. Okay, so now we have to do the keyframes. Luckily, we've done the keyframe thing a few times before. So let's see what happens if we just, you know, go through and do it. Okay. So let's see, here we have it right here. And let's see, let's go ahead and copy that and bring it down here. Okay, so now each of these objects obviously has a name, and the name is going to be MCID. No, the name is going to be random points duplicates I. Okay, MCI. So we want MC. Then we want I for all of these guys. So, oh, sorry. This is obviously different. Let me just go here. Let me copy this. There we go. Actually, first of all, let's go through here and remove all the names. 1 second. Now let's add in this guy. So let's do I dot, and then we're just gonna copy it in all of these guys. 1 second. There might be a faster way to do it, but that worked okay. Okay, so now we're gonna go down here and let's see. It's gonna be it's not gonna be make frame. It's going to be frame number. And let's go down here and do the same thing. Frame number. I have the window open today, or not open, but I have it kind of like the blinds open. So I just wanted to see if, like, how bright it gets at what time during the day today. So if it ends up being that it's too bright for you guys, and for some reason I left out the eye. Ah, shoot, you're right, I did. Thanks. Okay, so let's add in the eye bit because I am an idiot and forgot it. So let's go here. There. Okay, so now we're going to add this in on all these guys here. Which, of course, changes the spacing for all of these guys here. So let's do another, I think it's 4. Yep, good. So here, here, and there. Okay, so now let's try running Blender-P, see what happens. Seems to run just fine. Let's see if we have... Okay, so we have no particles here. We have... Okay, good. It looks like we have all the particles appearing. Fantastic. Now, granted, they are appearing incredibly slowly, and that's another thing we need to fix. So let's go through and do that. Okay, so now we have a situation where we have an interior resolution. So what I want is I want resolution, and then I want, I guess, step resolution. I don't know what to call it. So let's go down here. What do we have here? We have all of these guys being created. That's fine. What do I need? I need to render like 100 particles at once, or 1,000 particles at once, or something like that. I haven't quite decided how to do that, but the first thing I need to do, we have this guy in here, Monte Carlo. Let me go to Monte Carlo here, and let me return number from Monte Carlo. Okay, let's write this. Now let's go to Blender-P Determinant.py, and let's see. Yes, so now we have way more time frames, or time steps. However, this is super long. Okay, that's 1,000 frames, or 1,000, what is this? Yeah, about 1,000 something frames, right? So if we have about 1,000 something frames at 30 FPS, that's going to be, or 60 FPS even, that's going to be, let me think, 1,000 times 60 is going to be, wait, I'm going to do frames per second. Oh, we have to do 1,000 divided by 60, my bad. So 1,000 divided by 60 is going to give us, I don't know, something like 1,000 divided by, I'm bad with this, let me just do it. 1 second, 1,000. Okay, so it's going to give us 16 minutes? No, 16 seconds. Is that right? I thought it'd take a lot longer than that. 16 seconds. 1,000 divided by 10 would give you 100. Yeah, okay, so maybe that's right. It's not as long as I thought it would be. But that's still fine, because we're going to have way, way more points when we actually do the visualization. Let's open this up here. And you'll note how much faster this part of things renders. 1 second. So we have all these particles here. No particles yet. Yeah, 16 seconds is right. Okay, so let's bring it over here so you can see that the particles are being generated. And here you see that they're all being generated. So let's just go ahead and click the play button here. And you'll see here's the object being transformed. And then here are all the particles appearing. Now, in essence, there is an exterior cube around it. And that's where all these particles are coming from. And that is perfectly fine. Now, this is going to take a while. But again, we have to do one more thing. And that is make sure that all the particles are not appearing individually, but instead appear in groups of like 1,000 or something like that. That'll speed things up significantly from there. Am I on Adderall? Not that I'm aware of. What is Adderall again? I think Adderall is the one that does... Is that the one that makes you hyper, or is that the one that makes you sad? I'm not sure, but I'm not on either one, whatever that is. Sorry. Okay, so here's the transformation there, and then we go through and fix it there. Okay, so now what do we need to do next? We have the Monte Carlo guy appearing. Now let's go up here. Okay, so my guess is that we want an exterior loop here. So we have 4 eye in range. Yeah. Good. Okay, so this is what I want to do then. So for eye in range resolution, the one that you make you programming machine. Oh, I don't know. I'm not sure what that means either, but whatever. Okay, so now we have 4 eye in range here, and this is what I'm going to do. I'm actually going to go through and generate these particles a little bit differently than how I was doing it before. So let's go here and let's do 4 J in range, and I'm just going to say, if you made the outer box fit more closely to the transformed box, you would need less particles for the same error. Wouldn't you need less particles for the same error? If you made the outer box fit more closely to the transformed box, wouldn't you need less particles for the same error? What you're saying is the box on the outside. Okay, so my opinion is that we're pretty close at this point, but you're right. So let's go here and think about this real quick. M player. Yeah, this is the one I want. Okay, so here's what we have, and at the very end there, this outer box is just barely fitting within, or rather, the interior, the middle box, let's say, is just barely fitting inside of the exterior box on the outside, right, in terms of Y. In terms of this axis, the axis that is moving along this direction here, it's also just barely fitting in. The only axis that isn't really fitting in is this one over here, moving kind of diagonally between these 2 points there. And again, if you remember from the eigenvectors for this matrix, we have one that goes straight up, one that kind of goes straight along one diagonal, and another that goes straight along the other diagonal. So that's kind of why it does that. I think right now we're in a pretty good spot. Again, in the end, the particles are going to be generated much, much smaller. So let's go through. And let's worry about that now. So J in range, I'm going to say, why not? I'm going to say 100. No, that's 100,000. That's way too many particles. Let's just do 10 for now, just to show that it is working. Okay, so now I need to put an extra 4 spaces on each of these guys here, all the way up to this frame number nonsense down there. So what are we going to do? We're going to do that, set number. What do I want? I want from 412 to, let's see, 438. And then I'm going to put in an S. At the very start, I'm going to put in 1, 2, 3, 4, and there. Set no number. Good. Okay, so now we have this, and this should generate a whole bunch of points. One last thing I'm going to do before continuing here is when we make the initial MC spheres, I'm going to make them just a little bit smaller. So let's make them at 0.05. Wow, that did not happen the way I wanted it to. Okay, so now we're going to run blender-p, and we should see that it takes a little bit longer, but not that much longer. Let me see, 99, 99. Okay, so it might take a lot longer than I thought. That's okay. We'll kind of do something else for debugging in a second. It's fine. Give it just a second to run. Harkening back to the days where we'd spend the entire day on this channel just looking at simulations. Okay. Let's see. How many particles did I just do? I did 10 times 1,000. Let me think. What do we have here? I'm guessing you want enclosed boxes. Sides to be parallel with the axes, because if not, you should be able to fit it much more closely. I wanted the exterior box, the very last box on the outside, to be, wow, it's a lot of particles. But good, this is kind of what we wanted to see, right? So we have no particles here. Oh, actually, I guess we have a lot of particles there. Where are these particles coming from? Huh. Okay, let's see what happens. We're moving the simulation along. Oh, wow, this is super laggy. Okay, let's play it. Here's the simulation as it's moving along. Then we should see particles start to be generated here. Yep, Okay, we sure did. Now the question is, why are these particles here already here? Go ahead and pause it, and let's see what we have. This guy is number... Oh, I forgot we have thousands of them. Oh, shoot. Maybe there's a better way to do this. Let me see. MC 269.009. Weird. Okay, let's go here. Chances are this one was not randomly generated. 487.007. Why do we have... See, we have MC155. Then we have MC155.001. But... Oh, I see the... Duh. This is obvious. Okay, let me go here. Let me close Blender. It doesn't... There we go. Hey, Power4. Hey, Lucky Box. I'm guessing if you wanted... let me see. Want the closing box's sides to be parallel with the axes. No, it doesn't necessarily have to be that way. It's just how it ended up in this case. Because if not, yeah, we can in essence. But again, in this particular case, I'm just using the transformation we used before because we know that transformation quite well. So now we're going to do J in range. Instead of 10, we're just going to do 2. Okay, and this is going to be, let me think. What do I want? Let me go down here. And so this isn't going to be I. It's going to be I plus resolution. And actually, let me just do this up here. So I'm going to create an interior count. In count, sorry about that. And this is going to be equal to I plus J times resolution. And this should solve the problem we had before of creating multiple particles of the same, how do I put this? Of the same name. So let me go here and change this to in count. I'm gonna have to do this with all of them, so let me just go ahead and get rid of all the I's. Actually, why don't I just do this way? There we go. Okay. I think we're misunderstanding each other. Oh, sorry about that. I mean, I think you're saying, unless I am misunderstanding, is that you would like to make the very last outside box smaller. I thought that's what you meant, but maybe I'm wrong. So let's go here. Let's write, and let's go to the last Blender-P. This will take a second, but not nearly as long as the last one. Okay. So let's see what happens at the very start. There are no particles. Then we go to here, and now all the particles appear. Okay, just for sanity's sake, I'm going to go through and try it with 10 again. This will take a little bit of time. So let's go here and let me run Blender-P. And while that's running, and we're kind of waiting for the output, I'm going to get a quick sip of water. It seems to be going faster than last time. Okay. Still a little bit more time. I apologize for the giant gray box there. That happens. You know, this is a gray box channel. We got a bunch of gray boxes. It's a nice day outside. I can clearly see the ocean now. I mean the box you're generating the particles in. Thanks, that your fan. Okay, let me see. I mean the box you're generating the particles in. Yeah, that's the one I think I mean too. Let's go ahead and open it up. Unless we're misunderstanding each other, we are both talking about this giant box right here. The one on the exterior. And what you're saying is we can make the box smaller. And we probably can. I don't want to touch it right now because I don't know what the final matrix transformation will be, and a cube is relatively easy to work with. So, okay. So here we have the particles, and they should be generated. Wait, oh, there they are. Why did they take so long? Oh, it's 10 seconds after the exterior box is created. There we go. And now if we zoom in, you'll see we have a whole bunch of particles. These guys are in essence transparent. They should be anyway. Let's see what we have. 1 second. They should be, where is it? It should be here. Oh, wow, they are actually not transparent. I apparently did something wrong here. So let me see. I did transparency, didn't I? MCB use transparency. I did that, I thought. MCB.alpha. I did that too. Interesting. Okay. Why would this not do what I wanted it to do? So let's go up here and let's open up the Python console and let's see if we can do something with that. So I'm going to bring this up a little bit and let's open up the Python console. Where is it? It should be here. So what we're going to do is bpy .data I believe objects. No, materials. Sorry about that. Then we want MC blue dot 1 second. You know what I might have done? Let me go down here. Yeah, that's exactly what I did. Let's change this to a Y, this to a Y, and this to a blue, and this to a blue. Okay, let's try regenerating these points in Blender. Not as many this time since we're fairly confident that it's working. I'm just going to go through 2 iterations. 1 second. It's going to take a second to... There we go. Okay, so let me go up to the last where I generated these guys. Here it is. Instead of 10, we're going to do 2. Let's write it over here. And now let's go to Blender-P. Give it a second to run. And while it's running, I might as well resize... Oh, never mind. It's done. I hate it when my simulations take too quickly or take too little time. Whatever. Okay, so now let's grab one of these blue particles, and the particle should be transparent now. And it is. Okay, so when we actually render this, you should see that they're transparent. And I guess just to make sure this is the point, let's go ahead and do one last render. It should take significantly less time than it did last time. There we go. Look at me, understanding English. So we're going to do Blender-B-P, which means that it's going to be rendering just in the terminal. -B. And then while it's rendering, let's see what happens. Yeah, so obviously when there are no particles, the frames take significantly less time. So that's kind of why it's taking, or is much, much faster. Okay, so let's go up to the top and check the notes. We have figures, we have make MC spheres translucent. We did that one. Make particles invisible until generation frame. Did that one. So now we have to figure out if we're in the exterior box. And this is what's going to take a good bit of time today. Let's go ahead and run the last mplayer command. So this is what we have right now. I need to make those particles transparent in the center there. That's okay. Okay. So it should be... Oh. Okay. So here we have all the particles being generated. We can make them a little bit more translucent. And the other thing we need to do is make those particles that are in the center there not there. We should probably get rid of them. Okay, so let's go down to the bottom. And I'm going to make them super transparent. I'm going to make them like super duper transparent. I'm going to make them 0.25. Okay, and now what I need to do, since we created new spheres... Where are we? NC spheres. What do we want? Oh, I guess this is what I'm going to do. So we created the NC spheres. They're at the center. But we want them always to be hidden. So let's just go down here. At the very end here. And let's just hide them. So what are we going to do? We're going to say... what do we want? We created NC spheres. What did we create them with? In exterior, create MC spheres. Materials, diameter. Okay, so we called them MCR, MC blue, MC green, or whatever. So let's go here and say bpy .data .objects. Then we want MC. Actually, let's do it down here. So we're going to do bpy .data .objects. Then we want MC red. I think this is right. Yeah, totally right. .hide. Then we need to check this equal to true. Okay. Next, we're going to do same for MC yellow and MC blue. So I guess I'm just going to copy this line and change it up. If I remember to change it up, that is. Let's do this. I'm adding a new line in there and changing this to Y. Okay, and then finally I do it for blue. And go up here and change it for blue. Write this, and now we should have them have the center particles not visible. So let's do blender-b-p one more time. Let me make sure I wrote it. Now let's do it again. Okay, this again doesn't take so long, so I think this is okay. Give it a second just to render. And now after this, we can get started on the next part, which is not exactly easy. And it's determining whether we're in the interior box or not. So I'm going to show you what I mean by interior box, or exterior box, sorry about that, in just a second. So it should be like 82 frames or something like that. Yeah. Good. Now we're going to run mplayer, full screen it. And the particle is still there. Okay, but what I need to do is figure out whether we're in this exterior box. So we have this very exterior box, we have a very interior box, and we have a box in the middle. And I need to make sure that we're not in the box. Or I need to make sure we are in the box in the middle. So I need to do something that allows us to determine whether we're in that box or not. However, I apparently failed miserably at hiding those particles in the center because they are not hiding. So let me see, use transparency equals true, hide. Okay, let me open it up in Blender. I'm going to not render the movie. And let's open it up in Blender. So we're going to do blender-p. And we should see these particles in the center of the box right here. Okay, 1 second. I should be... Wait, why are you... What? Ah, I must have forgotten to write or whatever. Give it a second to do its thing. Totally forgot to write. Okay, so let's go here. But there don't seem to be particles in the center. Huh. Okay, let's move this box out of the way. I'm not seeing those particles at all. Well, that's weird. Why are they appearing at the render time? Let me see. I'm looking for MC red, blue, and green. MC red, blue, and green. Oh, here we are. Oh, it looks like they're hidden. What? Let me go through and do this one more time. So here's what I'm going to do. I'm going to get rid of this. Write that. And now let's try blender-b-p one more time because they're totally hidden in Blender itself. Oh, you know what I forgot to do? I know what I forgot to do. I forgot to hide them from rendering. So I hid them, but there's also this hide render value, which I totally forgot to do. My bad. So let's go up here and let's add that. So it's going to be hide render equals true. There we are. Hide render. And we have to do that for all of these guys. Up here. Render. And finally the last one. There. Okay, so let's write this, and if we do the last mplayer command, you'll see that the particles are still there. Yep, right there in the center. I'm talking about these little dots there. I don't want those dots to appear. So let's go through and let's get rid of them. Do it one more time, and this should get rid of them for good. Okay, and then after the simulation, we'll move on to the next bit, which is, again, determining whether we're in that middle box. Gonna be super fun. Woo! Oh, I'm tired. I guess I'm always tired. At least, you know, during stream. Okay, so what are we gonna do? We want mplayer, and you'll see, woo, the particles aren't there. Good, okay. So we're getting there, guys. I think this will turn out pretty good. Again, I'm going to have to lower the diameter of the spheres in the end, and I'm also going to have to increase their transparency one more time. So I'm going to make their alpha value like 0.1 or something like that in the end, but that's okay. That's for later. Vim tip, if you just want to copy line and immediately paste it, you do YY in normal mode. Yes, I knew about that trick at one point, and then I totally forgot about that trick. Thanks for reminding me. Okay, so let's go here. Now, how are we going to determine whether we're in that exterior or interior box? The naming convention is weird. I totally get that because we're like in the middle box here, but that's fine. Let's go and do page, new page before. Okay. Here's what we're going to do. This is the easiest way I could conceive of doing it. If there's an easier way, let me know. So we have this cube, and let's just, for the sake of the argument, pretend I can actually draw cubes. Oh gosh, I can't even draw lines. Let me do it with this guy. Maybe this will help. There we go, one box. Second box. Line. Nope. 1 second. Line. 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 Okay, there we go. Look at me. I can draw boxes. Woo. Okay. So each of these surfaces is some sort of plane, right? So that's a plane. Let's see. This is a plane. I don't know. This is a plane. So on and so forth. And the idea is that we can create the equation for the plane. The equation for the plane is very simply ax plus by plus cz equals d, where a, b, and c all come from the normal vector. Now, if you're not familiar with mathematics or calculus, you might not know how to do this. So I'm going to very quickly show you what we're going to do so that as I'm doing it in code, you guys don't get kind of confused because it's not exactly the easiest thing. So what we're going to do in order to find the normal vector is the following. If we have 3 points on the plane, here the plane being basically the board itself, right? What we do is we need to create 2 vectors on the plane by basically subtracting values. So we'll say one vector is here and another vector is here. And this is simply by doing the following. So we'll say vector 1 is going to be equal to x. We'll call this point 1, 2, 3. x1 minus x2. y1 minus y2. z1 minus z2. And we say vector 2. And I'm going to put an underscore under these guys. Is going to be equal to, let's say, x3 minus x2. y3, sorry, minus y2, and then z, 3 minus z2. Okay, so this will give us 2 vectors. Then in order to find the normal, we simply find the cross of v1 cross v2, and that'll give us a normal vector. It might just be linear algebra. Yeah, it probably is linear algebra. Sorry about that. When I looked it up last night, they said like some sort of calculus. I don't remember. Anyway, you're right. It is just somehow linear algebra. I just don't remember when I learned it. And this will give us the normal vector. Okay? With the normal vector, we will then have a normal vector with A, B, and C. Okay? And these will then be read into our equation for I'm going to put it up here. So ax plus by plus cz equals d. And then we have a question, how do we find d? And we can just plug in point 1, 2, or 3 to find d. So that should be relatively straightforward. What we need to do now is find basically the points which are going to be on the plane for us, if that makes sense. So we have to find 3 points that are on each plane, and there are 6 planes to work with. So this might take a little bit of time, but the way I see it is if I don't finish it here, I'm going to finish it tomorrow off stream. I don't see any reason, because this is just going to be a lot of kind of brute work. I don't see a reason to kind of do this on stream. What I'll do is if we don't finish it, I will do it off of stream and show you guys what it is that I did. If you guys are okay with that. If you want me to do it on stream, just let me know and I can do it on stream. That's fine too. No big deal here. In fact, if we do it on stream, there's one more visualization I need to do for the video that I decided not to do on stream because it's kind of easy. But if this one ends up taking over a day, we might do that visualization too. We'll see. Okay. So, you actually have 4 points? Yeah, we actually have 4 points, but we only need 3, I think. Yeah, because we only need 2 vectors to define the normal vector. So, as long as we have 2 vectors that are on the plane, we're fine. Ready-made for you, don't you? What do you mean ready-made? Okay, so let's go over here and let's open up this code in Blender. And what I'm going to do is, for now, I am not going to do the Monte Carlo. So I'm going to comment this out, write this, and let's do blender-p determinant.py. Okay, and this should just open up the box like we had before. In this case, we don't need the box, so let's go ahead and delete that. We just need these exterior points. Okay, so what are we going to do with these exterior points? You can clearly see with these exterior points, 1, 2, 3, 4, 5, 6. 6 planes. So what we need to do is figure out where all these points are on the plane. So what I'm going to do is I'm going to write this down on a separate sheet of paper, what the ones that we need. So let me very quickly get a pen, which I have failed to keep in my vicinity. I'm a horrible person. 1 second. Man, I like streaming with the blinds open. This is kind of nice. I can see the ocean out there. I can see my simulation right here. This is great. Okay. So I'm going to draw this out on my own. 1, 2, 3, 4. 1, 2, 3, 4. Okay, so let's see what we got. So this first point over here is going to be point. Let me see. Can we see the ocean? Maybe in a bit. It's still too dark. Let's see. Animation. What do we have? XYZ. What am I doing? I'm going over here. 0.001. 4.001. 2.001. 6.001. Okay, so let's do this then. Okay, so it's 4. 1 second. I think 4, 0, 2, 4, and 6. And then we have down here, should be all the odds, obviously. So it should be 1 back here. Oh, oops, I did not mean to do that one. So it should be 1 here. Yep, so this one should be 3, I believe. Oh, well, 1 second, if I can click the dot. 3. This one should be 5. Good. And this one should be 7. Oh, oops, my bad. 7. Good. Okay. So all the odds are on top, or all the evens are on top, all the odds are on the bottom. And for the record, if this is confusing to you guys because you'd expect it to be the other way, remember that this box did do a transformation, right? So it started here, and then it did the transformation. So it was 1, 2, 3, 4, 5, 6, 7, 8. Started at the top and rendered down. And so that's good. In fact, we should have, let me think. No, it should be okay. We actually set these positions initially. So at this point, we should be able to find all the surfaces without too much trouble. To do this, we need to read in numpy, which I already have in. So let's go here and let's start working on this function. Okay, so finding the bounds. We first have to find each of the 6 surfaces. Let's do here. Find these 6 surfaces. Now, I haven't decided quite how I want to do this. What I need definitely is a bunch of different vectors, right? So I need at least, let's see, at least 2 vectors per plane and then 1 normal vector per plane, right? So let's just go ahead and start by generating 1 surface and then we'll kind of go from there. So, man, my leg is killing me. We did a leg day yesterday and it is just Ah. Okay, so what are we going to do? Let's start with something simple. So we know that all of the even ones are on the all of the even points are on the top, and all the odd points are on the bottom. So let's do 4 I in range, and then we have 8 particles, so let's do 8. Okay, so now we have to generate each of these different variables. And what I'm going to do is I'm just going to put them all into the into an array, I think. Can I do a list of arrays? That's kind of what I want. Let's open up Python real quick over here on the side, and let's see what I'm allowed to do, because I have no idea. I'm really not that great with Python. So let's bring this, let's bring this down here. And let's see what we got. So let's run Python. I think Python 3 is what I'm using here. So let's do using NumPy as NP. Oh, wait, what is it? It's, oh, I have it up here. Import. Okay, import NumPy as NP. So let me do this. Let me do, how do I want to do this? We would do NPy. So I think it was, something.array. Let me go over here and check. I definitely wrote this down last night because I knew I was going to get confused. So, nope. Nope. Okay. It should be np.array. Okay, good. So, let's see what happens. It should be a equals np.array, and then we give it some values in here. So 1, 0, 0. Okay. Maybe they're commas. Oh, 1 second. Okay, so that works. So let's do a of 1, and a of 0 should be 1. Good. Okay, so next what we need to do is make a list of arrays. So let's see what happens. We will do b. Actually, let's just grab this npy.array. Let's grab b, and let's say this is going to be equal to 0, 1. And then we're also going to do c as, let's do 0, 1. Okay, so we have a, b, and c. Now let's do, I don't know, array. Yeah, why not? Let's just call it array is going to be equal to this. Then we'll say array dot append a, b, c, and let's go ahead and do array of. What happens if I just do print array? Good. Okay, so it is printing out. I realized that was horrible notation, but that's okay. There's probably an easier way to do this with NumPy. So I want, let me think, two-dimensional array with NumPy. That's what I want. So let's see if I can do that. 2D array NumPy. Two-dimensional array NumPy. And let's see what we got. N-dimensional array. Woo. Okay, so it looks like it's just NP. Let me see. Where are we? ND array. Where is that? Oh, type ND array. Let me see. How do we start an ND array? Array, ND array. I wanted some quick example code. NumPy. Let's see what we got. Okay, so it looks like the first dimension axis. Nope, array. Oh, it looks like I'm just allowed to do that. Let me see. So we'll do array. No, let's do D. It's going to be equal to the following. What did they do? A. Oh, wait. A.shape. NumPy.array. Type B, NumPy.array. Oh, that's what I want. Good. So it looks like I can just do this. NumPy.array of, let's do 1, 0, 0. comma, 0, 1, 0. Good. And data type not understood. Oh, maybe I need to do D-type complex. Let me see. Nope. 1 second. Does this work? Yes, that one works. So what's the difference between that and what I put in? Oh, okay. I forgot to put in... No. Oh, I see. Okay. So I see the difference. It's fine. It doesn't really matter that much. Now let me see if I can do b.append. Because I think we're going to need append. And let's append numpy. Screw it. I'm doing this with a list of vectors. This is what we'll do. It's fine. It's a little bit slow, but I don't really care that much. Okay, so what do we need? We need this. So what we need to do is find 3 points on each plane. So let's see, which planes are we going to have? We are going to have 4 points on every plane. And let's just do it. So we're going to go here. And for right now, I'm going to go through and say if, let's say I mod 2, so it is divisible by 2, equals 0. We're then going to say it's on the bottom plane. And just for now, we're going to do the bottom plane, and then we'll kind of work with all the other planes after we get one plane working. Okay, so what do we need to do? We need to say we can create vectors. So let's create a vector of each of these points. So we're going to say, actually, no, better yet, let's do it this way. We're going to say up here, what do I want to call it? I'm just going to say points, because I'm really original and I'm not good at naming things. And we're going to say points, rather, temp array is going to be equal to numpy.array of the following points. So we're going to need each individual position for each of these guys. So let me think. It was 1, 2, 3, 4.001. So it's going to have to be, let me see. I don't remember. Shoot. Okay, so let's run blender-p one more time. And I have to find the locations of each of these points. So let's go here, move the box over there, grab one of these dots, there we are, and let's get to the X location, which should be here. Yes, so the X location is going to be bpy.data.objects2 location. Okay, objects2 location. Well, that's weird. 1 second. bpy data object 7.001. Wait a minute. There we are. 3. I could have sworn they were just 0.001 before. I guess it doesn't make sense that they're 0.001, but that's okay. bpy data object 6 location 0 is going to be X. So let's go here and add that one in. So we want npy.array of bpy.data.objects. Then we want the following d. Then we want I dot location 0. That should be right. Yep, that's exactly what we want. Okay, and then we just need to do this for the other two. So we're going to do basically the same thing here. It's going to be bpy data objects I location 1. Oh, that was an I. And bpy data objects location 2. And this will be for X, Y, and Z. Then we close this up, and we do points.append temp array. Let's do temp array. Okay, so now at the end here we should have a vector of points, each of which points to a vector and that should be okay. Not points to, but you know what I mean. It shows us a vector. Okay, so now we have all the points. And now we just have to go through and determine which one's on each plane, which we already kind of did a second ago. So let's go through and work with the bottom plane. So here I'm going to say working with bottom plane. So basically we have to find the equation for the plane. So to do that, let's see. We're going to have to create two different variables. So far as I can see, we're going to have I guess, normal bottom. Yep. And we're also going to need evaluated bottom. Okay, there we go. So we have normal bottoms and evaluated bottoms. Good. This is not at all related to people in real life. Okay, so let's go ahead and do a cross product between 2 points and the np.array. In order to find these points, we know that they're going to be odd, right? So we'll just grab 2 points that we know are on the plane and go from there and do a cross product. So these are the 2 things we're going to need, but I don't need them now. We're going to say normal bottom, I do need one now, is going to be equal to the following, and it's going to be we'll say points. Dang it, I knew someone was going to go there. np.array. Oh, np.cross, I believe. Yep, I think that's right. Points of 0 should be... No, points of 1 and points of 2. Okay, I'm going to see if this actually runs. So let's go here and let's go print. And let's do the normal bottom. Let's go here. I think I just accidentally wrote and quit at the same time, but that's okay. And now let's run blender-b-p. So we're not going to open up in the terminal, just -b-p. Let me go down here. Now I'm going to put Monte Carlo back on. And let's do this. Okay, so we're at least printing out points. That's good. And they should all be the same point, right? Because it's all using the same values. So what are we doing here? MCY here. So we don't want to print that anymore. Now we're going to say evaluated bottom. And there's probably some better naming convention here. I'm not going to worry about it. It's going to be equal to any of the points on the plane. So since we have... Oh, oops. Oh, gosh. I forgot to do one thing. I'm an idiot here. Let's do this and let me do temp vector 1 is going to be equal to... Oops. Are we allowed to do this? Points of 1 minus points of 3. I don't know if we're allowed to do this. Temp vector 2 is going to be equal to points of 5 minus points of 3. And then we're going to do this and change this to a, what do I want? I want this to be temp vector 1, temp vector 2. One and temp vector 2. We had 2 points on the plane, and I was being kind of stupid there. We want 2 vectors on the plane. Okay, so now we're going to say evaluated bottom is going to be equal to normal bottom. Oh, this is way too long of a name. Way too long. Of 0 times. Then we want points of... I'm really not sure I'm allowed to do anything here. So let me do points of 7, 0, plus, and let's go down here and just copy this twice over. And change it up. I'm not sure what I am and I'm not allowed to do here. So let's do this. Let's do this. This is going to turn out way wrong. Let's do this. And let's do this. Oh, oops, my bad. I think in order to do this correctly, I just realized something. You can do this whole thing much easier. Apply the inverse of the transformation matrix to the particle's location, and then you can have the test used for regular axis aligned cubed. Let me think. Apply the inverse of the transformation matrix to the particle's location, and then you have the test used for regular axis aligned cubes. What do we mean here? So if we perform the inverse of the transformation matrix, what are we going to get? We should, unless I'm incorrect here, get the original point back, right? So if we perform the inverse, we should get the point previously. Then you can have the test used for regular axis aligned cubes. Yeah, maybe that is easier, but I'm not seeing how to do it right now. So I guess what you're saying is if we perform, let's see, if we go back and we generate, yeah, I'm not sure. I'm going to do it this way for now, and if we run into, if I can figure out what you mean, we can probably do it a little bit better then. Let's go here and let me write in Blender-P. Yeah, I didn't figure that worked. But this one's also not going to work. Yeah, that's what I thought. Okay, how do I continue in Python? How do I do a line break? Really? Okay, I guess I should have guessed that character. Here, there. Now let's run Blender-P. Let's see, what does it say? Temp vector is not defined. That is because I thought we were defining it there. So let me see. Oh, it's temp vector 2. Let's do Blender-B. It seems to be running. Okay, so let's go through here. And now let's put in a very simple if statement. Remove this line, and this line, and we're going to say, you generate the particles in the same coordinate system as your transformed cube. Okay, they are in the same coordinate system. They're both Cartesian. Let's go here and let me say, if, oops, sorry about that. If, now we need to evaluate a point. So let's go here, dd, and let me say, evaluated point is going to be equal to this guy right here, xx. So we have, yes, times points, but instead here, what we want is x, y, and z. So let's do x, y, oh, sorry about that, y, and z. If you apply the inverse of transformation matrix you use to get the transformed cube to the location of the particle, it'll be the same coordinate system as the original cube. Okay, I'm almost following you. So if evaluated point, let me see, is, what are we going to say? In this case, greater than, because it is the evaluated bottom. Let's go here. We're going to change the MC ID, and we're also going to say x count. One second, I think I have an underscore. Count plus equals 1. And then we return that. So let's run Blender-B-P. No, let's run Blender-P. Here we are. See what we got. Do we have any yellows? We have a couple yellows. Not quite what I was expecting. Okay, that's fine. Let me try changing it to this. Blender-P. So one second, I'll get to your thing in just a second, Gustorn. So now they should all be yellow. Yeah! They're all yellow. Good. Okay, so I wanted them all to be yellow because that means we've officially evaluated the bottom plane. Okay. Now let me see, gust run. So you can test against the original cube and it will be correct. Oh, okay, I think I see what you're saying. Wow, that's actually super smart. Okay, so we evolve a point, then we transform back. Yes, okay. So that means we have to perform the inverse of the... Yeah, that's actually super smart. I like that idea. So all you're saying is we take each individual point after we've randomly generated it, we go back, then after that, we check to see if it matches against the original point. That's really cool. Yeah, I like that idea. However, we do have to make sure it's invertible. And let me think. That just means that we should get the identity matrix when we multiply the transformation matrix. Let me see if we can do inverting a matrix in Python. Because maybe you're right. Maybe we could just make this super simple. Let's go invert. Let's see. Learn how to solve, tensor, invert. Compute the multiplicative inverse of a matrix. Yeah, that's what we want. I guess we could just read the matrix in. Yeah. That's a good idea. I like that idea. Okay, so we have some sort of array. Let's see what happens if we run the inverse. And then we're just gonna check this guy out. So let's go over here to Python. At this point in time, we know the matrix that we're working with. So let me go ahead and create that matrix. We're going to say D is going to be equal to, we're going to say matrix is going to be equal to the following. So what do we want? It's going to be 1, 2, 0. Then we want 2, 1, 0. Then we want 0, 0, negative 3. Okay, let's go here and there. And this should create a matrix. Now we want matrix. Let's say inverse is going to be equal to matrix dot inv. I think this is right. Maybe parentheses? No, what was it? Oh, inverse of A, my bad. So inverse of matrix. Inverse, not defined. Oh, it's numpy, I believe. Numpy dot. It has no matrix. 1 second, where is this? Numpy linalg invert. Okay, so numpy dot linalg invert. Okay, so now let's do, I guess, let's go ahead and print out inverse. So inverse is, it looks like it inverted it. So I guess let's just do this. Let's say, what happens if we do matrix? I don't know if this will work. Inverse. 0 point. Yeah, that clearly is not right. Let me think. How do we do matrix multiplication? Numpy. Numpy dot multiply. We should need the cross product, I believe. Or, no, that doesn't make any sense. Numpy dot multiply. A range multiply. Yeah, let's do that. So let's do numpy dot multiply. Yep. And we want matrix inverse. Oh, okay, that actually gives us the same guy. If you only do translate, rotate, and scale operations, it will be invertible. I don't know what you're doing right now though. I'm inverting it in Python. 1 second. I'm trying to figure out how to do this correctly. 1 second. So we do numpy dot, let me think. Well, I figured that numpy would have a way to go ahead and invert the matrix, right? So we created the inverse of the matrix, which should be linalg.inverse, I believe. And then we should just be able to multiply it to get the identity matrix. So I'm checking to see if that's true. Oh, it's just dot product. Is that correct? 1 second. Is it supposed to be the dot product? I feel like it's not supposed to be the dot product. It should be that matrix A times matrix B equals... 1 second, let me think. I need a quick sip of water, and then we'll go from there. Hey, Zivo25. We are working on basically the visualization of the determinant. So the idea is that right now we are trying to find the best way to basically evaluate where points are in space in such a way that we can tell if they are within some arbitrary axes. We always have defined element-wise multiplication. Okay, so let me try defining this differently with a matrix command. So let's do numpy matrix. And let's see what we got. numpy.matrix. So matrix is the following, and let's do it that way. So I'm gonna copy this, and let's go here. So we're gonna say matrix is going to be equal to the following, and let's do 2 0. Then we want 2 1 0. Then we want 0 0 negative 3, because that's the matrix we've been working on. Okay, so now let's do numpy dot inverse of the matrix. Oh, I'm sorry, numpy lenalg. Where are we? Inverse. Okay. Now let's try matrix times inverse. Okay, there we go. That's what we want. Thanks, Gustorn. Okay, so now let's see if we can do Gustorn's strategy on this particular guy. So the idea is actually incredibly cool. Because we have a pretty simple transformation that we're running here, what we can do is we can inverse the transformation. So each random point that we generate, we can invert back onto the original box and then determine if we are in the interior like we did before. And because the interior is incredibly simple, this should be relatively straightforward and much easier to understand, I suppose, in the end, than what we did before. Actually, this is super cool. I hope it works out. So let's go here. And let's go down here. And let's leave that if statement there. Now what we're going to do is creating... Let me see. Actually, I'm going to put this here. I mean, I would imagine it... Well, I don't know. Will it be faster? Maybe. I have no idea. We'll see. It doesn't matter anyway. It's in the end, it is less code and it's cooler code. So I want to see if it works anyway. So what are we going to do? Let's go ahead and create defining the transformation matrix. So here it's going to be matrix. It's going to be equal to exactly what we put down here, which should be the following. Good. Now we're going to say inverse is going to be equal to numpy.lenalg inverse of the matrix. Okay, and if you guys have any questions, comments, concerns, let me know, and I will totally get to those as soon as I see them, and inverse. Okay, now we should be able to transform individual points. Yeah, it won't be faster? Let me think. So the other one, we've got to define each evaluated plane, right? Yeah, maybe not. Let me see. We'll see. It's fine. So we have NumPy linear algebra inverse. Now, what else do we need to do? I suppose what we need to do is figure out a vector to work with. So what we'll do is we'll say the following. Let's go up here. Matrix.inverse, linear algebra, NumPy multiply. Where were we before? Okay, so let's see what happens. Can we multiply the following? I think B is already an array. So let's try inverse. Oh, that wasn't what I meant to do. Inverse times B. I'm sorry, I think it's B times inverse. Okay, good. So we can't multiply B times inverse. However, what's A? Let's try A times inverse. Yeah, that's what I want. Good. Okay, so now we have to basically create an array like we did before and do the multiplication. And let's see what happens. So the array should be pretty easy to do. Let me just go ahead and pull one up. So we have array. Here we are. So now we're going to say vector. I'm going to call it random vector. Is going to be equal to numpy.array of the following. And we want to do x, y, and z. Okay. Now we're going to say now transforming back and checking against original cube. Okay, so let's see what we got here. We need to do transforming back and checking against original, forgot now, cube. Okay, so let's see what we got. We have the random vector, we have the matrix, so let's go back and check the point, and then let's see what we got. So we're going to say new, I guess we could keep it as random vector, is going to be equal to random, let's say point is going to be equal to random vector times inverse. Okay, now we're going to go down here and we're going to evaluate it. Basically by the same thing we did before. If all these guys are here, except in this case, x, y, and z are a little bit different. So instead of x, we're going to say point of 0 and point of 0. Okay, then we have this. Let's bring it down to the bottom. Oh, sorry about that. And point of 1. And point of 1. 1 second, I will get to that comment in just a minute. Point of 1. And then finally for z. And I think we're going to have to continue these lines. So let's go to point of 2 and point of 2. Okay, and let's go ahead and continue all these lines so I don't accidentally do something stupid here. Okay, there. Let's see, can you recommend any ideas for some projects to get out of the intermediate stage? I know at the moment C++, C with STL, Python, JavaScript, but I don't know what projects to start. A project that would make me some time to finish where I could learn more. Recreational, let's see, I recreated games like Tic-Tac-Toe, Tetris, Snake, Hangman, but they're kind of boring and I want something complex. So Zivo25, first of all, I would not consider myself out of the intermediate stage either. I would consider myself a moderately, I'm a decent programmer. You know, when it comes to it, I'm okay. I'm not the best, but I'm okay. So I'm still in the intermediate stage myself. What I would say, and again, this is just advice from me, is I would say just, again, like Gustron said, find something that you're interested in. For me, it was physics. I enjoy doing physics algorithms and things like that, so this kind of stuff is perfect for me, where I just kind of, basically, I open up a book. Numerical Recipes in C++ is one book, but I don't use it so much because of their licensing, but it is a book that I have. I open it up, I look at an algorithm, I implement the algorithm, and I just kind of learn about it from there. And, you know, I also started streaming and just kind of saying, hey guys, let's do some physics on Twitch. Why not? To this day, I think I'm one of the only physicists who does numerical physics on Twitch, so I think that's pretty cool. So we're going to do determinant -p, and it looks like we've got an error. What is it? It's going to be if 0. Oh wait, what do we have here? The truth value of an array with more than one element is ambiguous. Use any or all. 1 second. Graphics is hard. That said, graphics are quite challenging. I've learned that throughout the past few days. So let me print out point. Let's go here and let's print point. Let's write this and let me run -b -p so it doesn't open up the GUI. And And let's see what we got. So it looks like the point, it does indeed have a point. That's good. Now let's see if we can just print out one point. Because it doesn't like that evaluation we had later. Let's go here and let's run this. And it looks like what we need to do is 0 of 0, which is weird, but no. Interesting. What do we need to do? If we print out the point, let's do blender-p, we get 0.6942. Now, how do we pull out one of these elements? Let's go up here to our Python code, and let's see, we have, what did we just do? We just did it a second ago. It was a times inverse. So let's call it something. We're gonna call it point. It's going to be equal to a times inverse. Okay, now we want point. Oh, point. This is a channel I got in quantum computation, which I had no interest in before. Try broadening your horizons. Ah, actually, that's great, Gustorn. That's nice, Simuleus. I think I'll have some good algorithmic books too. Until now, I did algos only competitive programming contests in my country and online contests. You're probably better coding than I am, Zivo, so I don't know if I can help that much. But Gustorn is definitely a person to talk to. He's very good with this kind of stuff. So let's try to print out point of 0, point of 0, 0, point of 0, 0, 0. It's all printing out the same thing, and I don't understand how or why. So how do I pull out an element of the matrix? So let me see. Let's see, how do I pull out an element in the matrix? So I want, reading elements in matrix numpy. Let's see what we got. Item. Is that what I need to do? Ren int item of 3. Let's do 1. There we go. It seems item of 1 did what I wanted. So if we do item of 0, that's what I want too. Good, okay, that'll do. Let's go down here and let's do that. So if point of 0, this is not point of 0. So let's go ahead and remove each of these guys. And this guy down here. And now let's just add in item of 0. And let's add it into all of these guys, and then we'll fix it in a second. Oh, oops, my bad. Point of item of 1. That one works better. Let me see. Point of 0, 0. Oh, good. Yeah, thanks. That one does look a little bit nicer. 0, 0. So then it should be 0, 1 for the next one, right? Yes, good. Okay, so here we go, 0, 0. Wow, I'm screwing up miserably with this. 1 second. Okay, so now let's do this here. 0, 1. And this here. Then 0, 2. Fine, I will keep it similar. And 0, 2. Okay, now let's see what happens if we write this, go over here to our console and run blender-b-p. Seems to be running, it is printing out stuff. I know why it's printing out stuff. It's printing out stuff because I told it to print out stuff. So let's remove this. Okay, so now we've inverse transformed it. We've checked to see if it's in the interior box or the middle box. So now let's run blender-p. And let's see what happens. Blender-p. And it looks like it actually worked. Except for the fact that the middle box is now not red anymore. But that's okay, that's a super easy fix. That's crazy. I really like this. Sure, admittedly, there might be a faster way, but this is really cool. I really like that. That's neat. Okay, so what do I need to do then? I need to go in and in the Monte Carlo simulation, I need to move in interior after in exterior. And yeah, I realize that's kind of sloppy, but hey, this channel is kind of sloppy. So let's go here, right? And let's see what happens. Blender-P determinant.py. And we should see 3 different sections. We should see a clear red section in the middle. There we go, an outer yellow section and a final outer blue section. All right, that's pretty exciting. So now what we have to do is generate thousands upon thousands of points, which is super easy to do. And we have the areas already. Yeah, this is good. Why do you prefer Python? New to this channel? Actually, to be totally completely honest, we only use Python when we're doing visualizations like this. So yeah, that's exactly why Nimthura hit the nail on the head. I don't know why I only remembered that today. It's literally what you do in ray tracing. Oh, that's fine. I'm very glad you remembered because that's actually incredibly cool. In fact, I think when we did the ray tracing a while ago, we mentioned this and I didn't understand it at the point, but I think that's really clean and crisp. That's super cool. Okay, what do we need to do? We don't need to find bounds anymore. This made the code incredibly easy. Now, what do I need to do? What I'm going to do is I'm going to change this to 10. And I'm going to render a quick video just to see what it looks like. So let's do Blender-B-P. And let's see what we need. Right, this, go down to the bottom, and let's do render movie. And let's see. Okay, give it a second to render this guy. It'll take a little bit of time, I'm not gonna lie. The first 80 or so frames won't take so long, but after that it's gonna get a little bit heavy. In fact, I fear we may not be able to actually do it in time. Let me just see how long this takes. Ooh, maybe this is a horrible idea. This might have been a horrible, horrible idea. But yeah, Nimthura's right. There are a good number of Python libraries that work very well for scientific computing and things like that. That said, if you're doing real computational work, you know, like work that you do on supercomputers and things like that, you may use Python, but chances are if you're really worried about optimizing things, you're either using Fortran or C++, or CUDA, which a lot of people have getting into. Yeah, I think you're right. This is gonna break. Which is great because I can no longer cancel Blender. Okay, well, we'll see what happens. Maybe I need to lower the resolution of the interior spheres one more time and make them like interior cubes or something like that. But we got up to frame 80, no problem. 81, yep, sure, we're getting there. 82. Maybe we'll be able to finish in time, we'll see. 84. Actually, this is much faster than I thought it would be. Oh, this is super exciting. Yeah. Okay. I think it's significantly faster than the last time we did the rendering, because the last time we did the rendering, we had significantly more points for each particle. So I think we might be able to get it done in time. That's super cool. Okay. So once we show this video, we'll then move on to the next step, which is actually finding that ratio between the two areas, which isn't going to be so bad, right? We have the total number of points in and outside of the box. We just have to return the total number of points. Yeah, I was honestly expecting it to be much slower, but I think we're almost done. I think we have like one more frame left. Let's see, we did 10 total frames. Maybe that's it. Maybe that's all the frames we need. Yeah, there we go. Okay, let's open up MPlayer. And let's see what we got. So here's the box transformation. Oh, I screwed that one up. Here's the box transformation. Okay, that doesn't look so bad. We need to, again, lower the size of the particles. And we need to make them even more transparent. But in the end, we can see that it's here. Everything that we need is here. We have the transparent particles, we can see the inner red, we can see the outer yellow. Again, if we just make the particles more transparent, make them a little bit smaller, and add more of them, we're set. Oh, that wasn't what I wanted. I want one frame before that. Okay. Yeah, so we need to make the particles a little bit more transparent, but that's okay. Nimthura, what we're doing right here... what we're doing right here is we're doing a visualization of the determinant. So the determinant is something that people typically learn in mathematics class, but they don't typically understand. Well, okay, it took me a while to understand what it actually meant physically. And here what we're talking about is a transformation of a matrix. So we start with a box. So here's what we do. We start with a box here. And then we perform a matrix transformation to get to here. Something like this. Then what we do is we add in the other box, the box that we started with, and an exterior box here. And then we perform a Monte Carlo integration to very quickly show that, how would I put this? To find the areas or the volumes of the boxes. Then we find the ratio, and that ratio should be equal to the determinant, which I think is super cool. So what we're doing here is basically a visualization of that. And we will be using this in my next YouTube video on Laos OS. So if you're interested, I can give you a link. If you're not interested, I won't give you a link. But it's actually, I don't know. I think it turned out really well. Obviously, there's more left to do, but it's turning out really well. Okay, so now the next thing we need to do is actually find the area of the two boxes. So because what we've been doing is we've been returning the interior count and the exterior count. Right before returning this function, we can actually print out the areas. So what I want to do is actually print this to a file so that I can go from there. Zivo25, I do not actually use a chair. In fact, my chair is back there, which you may be able to see in the camera. It's, yeah, sorry, Gustorn. I don't know what the commands are like. But let me think, what am I doing? Oh, you're going to add a command for the YouTube channel. That's actually a really good idea. I didn't think about that. Okay, so now what we need to do is actually print these new areas to a file. It's going to be a super easy thing to do. Shouldn't be that big of a deal. Okay, so at the end here, we will go ahead and do that. No, I don't use a yoga ball. This is going to sound really cheap and stupid of me, but I actually have a stool that happens to come up to exactly where my bum is. So when I'm standing. So I just sit down on that so that I don't ever have to change the standing desk. I should have probably gotten an actual chair, but I was so cheap when I was making this desk. Like this desk, I made it for like, I think like $40 or something like that. So, woo, can I do that? I don't know if I can do that or not. Not on IRSSI. Oh, I can. Yeah. Okay, that's great. Okay, so what am I going to do next? Is it user? Really? Does this link work? Open link. It does. Wow. I thought it wouldn't work. Anyway, that's great. Okay. So we need to print this to a file, and that's going to be it for the day. However, I cannot remember how to print things to a file in Python. I know it's super easy, but I always forget. So let me go here and print out to a file. Don't. Ah, thanks, man. I appreciate it. Totally a coincidence, because I don't think there's any situation where I have ever heard that phrase. That's a coincidence because my chair comes precisely up to my bum as well. I've never, I don't think, heard that phrase before. What am I doing? I want to input output here. Okay, string hello world print s. I want to output to file. Okay, how do we, no, open, that's what I want. F equals open, there we go. Let's go. So we're gonna go here, print I. Do I need to print I? Whatever. F open output.text, and we're just gonna say out.dat. No, I already have an out.dat. So out dot, here's what I'm gonna call it. I'm gonna call it, areas, volumes, .dat. Why not? Okay, so now we have to print something to the file, and I think, let's see, sd out, print, f.close. So now we want to do file. I can't do out.jpg, not at this point. So we're gonna say out file is what we're gonna call it. Okay, so equal open, and then I think it's write. Isn't it write? Write Python. Control F, write. Let me see. Down here, write. For X in range, print. Here are two ways to write to a table. Do not write. White on black text editor. No colors inside. I think it would be dead like that. I'm sorry, Zivo. I know a lot of people come to this channel and they kind of get mad at me for that, but that's okay. What am I doing? First, we need to figure out what the volumes are. We have an in count and an out count, and then we have an area of the box because we have box lengths, right? So what we need to do is say we have box length. What am I saying here? We have in count, we have out count. So we should be able to do this. Interior volume, let's say in volume, is going to be equal to, let's say total count. Yes, we have total count, we have in count. So it should be in count divided by total count times box length. And then we have, thanks, Gustorn. Again, I totally forget how to do this all the time. Now we do X volume. It's going to be X count divided by total count times box length. And then we do finally volume ratio. It's going to be equal to X volume divided by in volume. Okay, this is going to be really rough, and it's probably not going to return what we want, but that's okay for now. So volumes.dat, what are we doing? With open volumes.dat as file, out file. Okay. Let me see if I can figure this out. Now we just have to write it to a file, right? So now we do, gosh, how do we actually do the writing? With open, Control F with open, here we go. Read data equals SF. I want to do output though. 1 second. F.write, thanks. So we're going to do outfile.write. And I guess we just write the three of them. So I guess we'll do invol, xvol, and volume ratio. Oh, no semicolon. Let's go over here and let's not render the movie. Let's see what happens if we just run it as -b-p. Okay, give it a second to do all the points. This is again 10 times 1,000 points, so 10,000 points. This is a good number of points. I think in the final simulation, I will have significantly fewer points, but that's okay. I'm actually super happy with how this is turning out, guys. I was expecting it to bomb something today, but you know, Gustorn gave us a good idea. I'm sorry, I use C++ regularly, so I don't know, I add semicolons to everything. Okay, give it a second to finish running. And again, we're not rendering this time. We should just output the volumes. And we'll see how far off we are after that. We know what the eigenvalues are, so we should be able to find the determinant pretty easily. And now we're going to see how far off we are with this simulation. But we have to wait for it to finish running. And of course it broke. Great. Let me see. Error right takes exactly one argument. Oh, dang it. Okay, so let's just do the following. Instead of writing it like that, let's just do this. It says it takes exactly one argument, but I'm not sure. Okay, so I'm gonna do this. One second. Okay. Out file. .write. The following. Let's see what happens if we do this. Except this time I'm probably gonna run it with fewer points. Let's just run it with 1,000 points. Blender-P. Okay, so it again broke. Right argument must be a string. Okay, so let's do, how do I turn this to a string? I guess it's just str. Right, must be a string, but what line did it break on? Let's ls here. Let me go into volumes.dat. Okay, we wrote one down. Good. Okay, so now what do we need to do? Let's do this plus, can I do a tab? Don't know. Okay, I will totally do that. Again, guys, I totally apologize for not knowing Python very well. This, and then we do that, and we say dot format, and we want invol, xvol, volume ratio. Now let's go ahead and delete these lines, and let's go to blender-b-p. That one seemed to work, so now let's go into volume.dat. Oh, VO. VI. And we have 0.334. Is that right? Invol, xvol. I'm not sure. Let me think. Something happened here. The in count is somehow greater than the exterior count, which it shouldn't be. Should not be at all. So I think I did something wrong here. And I'm not sure what. So let's see what we got. Because the exterior count is clearly bigger, right? So here, let's go here. Right and quit. Let me run the last mplayer command. Okay, so clearly, this exterior volume, wait, 1 second. So the volume that is yellow is clearly bigger than the volume that is red, right? So you would expect that the exterior, the yellow count is bigger than the red count, but that's not what we're showing. So I need to go through and figure out why that's the case. Okay, so let's see what we got. Thanks, Nimthoro, for the suggestion. Gust runs is currently working fine. I'm not gonna rock the boat at this point. Okay, so what do we have? Place duplicates, in count, x count. Do I set x count? No. Okay. In exterior, your in count doesn't do what you think it does. Okay, maybe that's true. Let me see. In interior. 1 second. Do you guys hear that? Maybe you don't. There's a siren going on outside. You should count them inside in exterior and in interior. I think I do, don't I? Yeah, I totally do. Let me see. In interior, in count +1. Do I count them at any time outside? Let me see. In count. Oh, oops. My bad. No, there was just an ambulance for some reason. I hope everyone's okay. So let's say, instead, let's just change this to count, because I don't think I just used count. And let's change these guys to count. 1 second. In exterior and interior, and let me see. What does this need? It needs in count and x count. So actually I needed in count and I needed x count, but there was something else I needed in count for. Count is equal to this. Ah, here it is, down here. Okay, let's write this. Now let's do blender-b-p. Okay, it broke. MC1 not found. bpi. What do you mean it's not found? In count, x count. 1 second, I'm thinking here. MCID. MCID is MC blue. In count, x count. Let me think. bpi data. Wait, why didn't it work? Okay, place duplicates. Oh, it's because of that. I missed one. Let's change this to count. Now let's go to blender-b-p, and this one should work. Good. Okay, now let's check the volumes, and it looks like we're getting the same guy both times. Nope. Okay, so this is a little bit different. Okay. Is Romania on a completely different time zone than the rest of Europe? I've got a friend here that's from Romania. He's pretty cool. Okay, so what are we doing? That sounded really patronizing. I didn't mean it to be that way. Okay, in count and x count are for some reason giving us the same value, and they shouldn't be. Okay, so we change. Let me see. Where do we do x count? Okay, so if x count, if it's in exterior, X count plus equals 1. In count is equal to in count plus 1. Just for the sake of notation, let's change this also to plus equals 1. Okay, where else do I change in count? It's there. It's there. Okay. So I think I screwed up somehow. Let's look at the visualization one more time. Let's see. It's going to be mPlayer. Okay, so here are the 3 boxes. Yeah, clearly there are more in one box than the other. Okay. Let's see what we got. MC, in count, X count, in count, divided by total count, invol, xvol. Man, I'm not seeing what I did wrong here. Let me go ahead and write this. And let's see, let me run it one more time, except this time remove volumes.dat. And let's see, blender-b-p. And let's see. You should return either 0 or 1 from in exterior and in exterior, and add those to in count and x count in your Monte Carlo function. Let me see. Volumes.dat. Yeah, they're clearly the same. Okay, let me see. Okay, yeah, let's do it that way. It's cleaner that way anyway. Okay, so we set MCID equal to this. Let me see. So we need to return the MCID definitely. In count plus equals 1, exterior count plus equals 1. X count, in count. Darn. Okay, let's see what we got. So what I'm going to do is I'm going to try Guster and suggestion of this, and we're going to say X count, count, sorry about that, plus equals, and I'm going to say, 1 second. Oh man, I messed up that one. I'm going to call it eval for now. And let's go here and just change this to eval. And then we'll go down here and do in count. Plus equals eval. Okay, and change this to eval. Okay, let's go down here. And instead of in count plus equals 1, we're going to set eval equal here. Eval equals 0. Eval equals 1. Oh, is it? Maybe it is. I'll change it in just a second. Because you're right, I shouldn't use that. Let's go here. Eval equals 0. And then we go down here, instead of doing x count plus equals 1, we say eval equals 1. It's probably going to break. Or not. Let's see what we got in volumes.dat. We're still getting the same volume. Okay, so let's change not eval. Why not? I guess I'll change it to inbox. Okay. Oh, change it in the return? Yep, fair enough. Sorry about that. Inbox. And where are we? Inbox. Blender-B. And let's see what we got. VUI volume.dat. Okay, they're clearly different. And more than that, we're getting 9. Exactly 9, which is beautiful because we know from previous stuff here, when we did the visualization of eigenvectors, we had found the 3 different eigenvalues. And you know what's super cool about this? Those eigenvalues were 3, let me just check to make sure I'm not saying something wrong, were 3, -3, and -1. If we multiply 3 times 3 times 1, we get 9. So the ratio of the volumes is exactly 9. Absolutely beautiful. That is fantastic. Okay, with that, guys, I'm very happy with how far we came with this, and it is almost exactly 7 o'clock in the morning, which is the time I typically end the stream. Someone asked if they could see the ocean. I guess I'll show you my view in just a second, but let me first go ahead and commit this to GitHub. So we're going to do git commit determinant.py. We're going to say -m finished simple visualization of determinant small, I guess, visual changes remain. Good. Okay, I'm super happy with this. This is good. Okay, so now we're gonna do git push origin master, and you guys will have this available to you guys on github.com. So I'll show you guys where that is. Simply go to my stream right here, scroll down a little bit to info, click at the very bottom to github.com right here, bring you to my GitHub account, Simuleos, and the last change will be in visualization. Where are we? Determinant. Here, determinant.py, and that's going to be where it is. Okay, so this is the latest file there, and let's see what else is left. I can't think of anything. I think that's about it. We've got a few things we need to do to make the output more visually appealing, but you know what? That's something I can do on my own. That's not something I need your guys' help for. You shouldn't declare a variable with the same name in the inner loop as you did in the beginning of the function in exterior. Yeah, you're right. I didn't know if Python would allow me to do what you can do in C++ with like an ampersand sign, and so I just kind of tried that. And that's fine. I should have recognized that. Anyway, guys, I guess that's about it for today. So someone asked if they could see the ocean. It's really not that great of a view, but I figure why not? I'll just kind of show you guys the view that I do have. 1 second. And that's that. Sorry about that. I'm sorry, okay? It's a small view. That's about it. I know, right? Parking lot. Anyway, that's about it for the day. Have a fantastic day, night, afternoon, morning, whatever time it happens to be your time. And I will see you around next time for the next episode of Simuleos, where I think we continue working on Huffman trees. Either that or we do the next visualization of determinants, which is basically a multiplication of the eigenvectors. I have an idea of how to do that. So guys, thanks so much for watching. And actually, let me see something. Am I allowed to do this, where I just pop this down there? Can you guys see the ocean there? Why not? Sure. There's the ocean view. Fantastic. I could actually just set it there instead of doing what I was doing before. There's a screen in the way, but that's okay. You guys happy? Anyway, guys, I'll see you around next time. Have a fantastic day, night, afternoon, morning, evening, whatever time happens to be your time, and we'll go from there. So thanks again for watching, and see you tomorrow. Bye, guys.